Alright, in this video we will be continuing our much requested Tinkercad Circuits Lab series with op amps, or operational amplifiers. These nifty little integrated circuits that can do all sorts of things like, as the name implies, amplify a voltage, or other cool stuff like differentiate or integrate, add, basically doing math with analog voltages without needing to run any code or use a microcontroller. So if you are just joining us, this series is a companion to my Intro to Circuits playlist, which goes through the circuit diagrams and math and equations behind a lot of the common circuits you would see starting in an intro physics class with Ohm's law and resistors, and going up into some things like RC filters and op amps and transistors that you would typically see in an intro electrical engineering class. Again, these videos are just showing the schematics and going through the derivations for many of the equations. This companion series is building these circuits on a virtual breadboard in a free online circuit simulator called Tinkercad Circuits that just runs in your web browser, and again lets you build things in this breadboard view as opposed to the schematic view that you would typically get with most circuit simulators. So as with the other videos, I am going to be walking you through building the circuit from scratch step by step in the browser. The first thing we're going to do in Tinkercad is search for an op amp, and that is going to bring us to our first caveat. Sorry, the search was a little laggy there. That Tinkercad does mention this is the 741 operational amplifier. There are tons and tons of op amps out there with different part numbers that are going to have different specs that you would need to look up in the datasheet. We are just using this kind of generic one in Tinkercad. We could go look up the datasheet for the 741 if we needed to, but we're not going to worry about the specific specs of this op amp too much. Like most other integrated circuits in a dual inline package, this chip is designed to fit across the gap in the middle of a solderless breadboard. So first thing you're going to want to do if building one of these in a lab is saddle your op amp right there across the middle of the breadboard with the notch or dot in the top of the chip facing up or towards the top. So the pins on these, and again, you could go look this up in the datasheet, are labeled starting with number 1 in the top left and going counterclockwise. So this is pin 1, 2, 3, 4, 5, 6, 7, 8. And right away, this is where a lot of students get confused, because when moving to op amps from things like resistors, the schematic or symbol used for these in a circuit diagram no longer looks like the physical part. So if you watched the other playlists, you'll see that we're using a triangle symbol for an op amp with 2 inputs on the left and output on the right, and then there are external power connections for the op amp that we don't usually draw in the circuit diagram. They are just sort of implied, and that is different from this rectangular chip with 8 pins on the left and right. So if we mouse over in Tinkercad, it is nice enough to give us these little tooltips that tell us which pin is which. But again, I've seen a lot of students just get confused because, again, with things like resistors, well, the physical resistor is just a little part with 2 wires, right? So the squiggly line or zigzag line used for the circuit diagram for a resistor that just has 2 wires coming out of it kind of matches up with the physical resistor when you're building it on a breadboard. Same thing for a capacitor or a diode or really any other part that just has 2 leads, but it gets confusing when you're making the leap from this triangle symbol to, whoops, wrong browser tab, this rectangular chip. So that's something we'll want to be careful about right from the beginning. And since I mentioned the datasheet, I did pull this up in another browser tab here, because if you were doing this in a physical lab, Tinkercad kind of spoils you by telling you which pin is which when you mouse over, but you're not going to have that in a physical lab. So here in the datasheet, again, we have the schematic view there, and we have to scroll down and we will see the actual pin out. And we see this one actually comes in a circular package or a rectangular package, and you can look here and see what the labels on these pins are, and then you have to kind of go back and forth to see how they correspond to the circuit diagram. So again, if you're doing this in a physical lab, you would need, or even if you're doing it in Tinkercad, it's good practice just to look up the datasheet for the 741 and look at this pin out where we have an offset pin that we're not going to be using. I didn't really cover that in the theory video. An NC pin, which stands for not connected, so that just isn't used for anything. Another offset pin we're not really worried about. So there's really just going to be 5 pins we're worried about in this video. We have the inverting and non-inverting inputs. Again, if we go back to our diagram here, that corresponds to the inputs we show in the circuit diagram. We have the output, which is going to be our amplified or differentiated or whatever it is voltage, and our two power pins labeled V plus and V minus here. And those are what we are going to talk about next when wiring the op amp on a breadboard. So again, for starters, make sure your op amp is straddling the gap in the middle of the breadboard. Don't do this, because another thing Tinkercad spoils you with here is showing highlighted in green which holes in the breadboard are connected to each other. So if you put the op amp all over on one side of the breadboard like this, then you are short-circuiting the pins that are in this row, and you don't want to have it 90 degrees like this, because again, you're shorting pins together, and well, technically you could build the whole circuit upside down like this. The chip will function just fine like this. That is an easy way to make mistakes. You usually want the chip oriented kind of like you're reading a book, so the writing on the breadboard is upright facing you, and the up or top part of the chip. And if we go back here to the datasheet, we see pin 1 is at the top left when that notch is on the top. All right, let's connect power. This is something that is usually new to students when working with op amps, so we're going to do this slowly and carefully because op amps are typically run with a split positive and negative power supply. And if you are working in a lab with a benchtop power supply, it may have 3 terminals for ground, positive, and negative. The power supply in Tinkercad just has a positive and a negative, so we are going to chain 2 of these together in series to create a split positive and negative power supply where the positive terminal of one is connected to the negative terminal of the next. So these are in series, and that's going to be our ground or reference or 0 voltage. And then we are going to set it up so this one is positive relative to ground, and this one is negative relative to ground. And again, if you have difficulty understanding that, I suggest going over to the circuits playlist, and somewhere in here I have a video about ground and what that means kind of as a reference voltage in circuits. Again, sorry, I forget which video that is here, but it's in there somewhere. If you don't get the whole idea of moving ground and how voltages are referenced relative to ground. So go watch that first, but physically to connect 2 power supplies here in Tinkercad, we're going to start out like that with 2 of these benchtop power supplies. And then this gets a little tricky when we're looking at the breadboard buses, because again, most breadboards, unless you're using a lab that has a breadboard with 3 buses on each side, are just going to have a positive and a negative, or a power and a ground bus. So this breadboard in Tinkercad isn't really set up to have 3 different voltages, so positive, 0, and negative. So you kind of have the choice of how you're going to do this. I'm going to show you one way to lay it out. This is not necessarily the right way. So what I'm going to do actually is delete this wire here. I'm going to connect the ground bus on one side of my breadboard to the positive bus on the other side. Now, just doing that on its own, sometimes students get confused and say, oh, isn't that going to create a short circuit because this one's positive and this one's negative? Not if it's an externally powered breadboard. Some breadboards do have internal power where they actually plug into an outlet and kind of have their own internal power supply, and then yes, you would need to worry about creating a short there. With this type of breadboard, just connecting a jumper wire there doesn't do anything because this doesn't have its own internal power. It is not powered until I connect an external source like a battery or one of these benchtop supplies. So I am going to imagine if I could just take a Sharpie and scribble off the negative and the positive there and just write 0 or a ground symbol. I'm going to use these 2 buses as my central ground supply. And I'm going to connect the terminals of my power supplies, which I had previously done, just connecting them directly. I'm going to connect them through these 2 buses. So again, that's connecting these in series. I'm going to use black to represent ground. So again, just imagine that I could either write 0 here or change this line black. I can't edit it in Tinkercad. And I'm going to connect the positive voltage from this one to the power bus on this side. I'm going to make that red. And then I'm going to connect the negative voltage from this one to the negative bus on this side, and say I'll use a 3rd color for that. I'm going to make that blue. So without doing anything or connecting anything to the op amp, say I'm also going to connect 2 multimeters here just to demonstrate how these are connected. So I'm going to have a multimeter here, and both multimeters I'm going to reference their negative terminal to ground. This one is going to be measuring that positive voltage. And this one is going to be measuring the negative voltage relative to ground. So you'll see what happens when I turn the whole simulation on here. So the positive terminal from this multimeter is going to what I have set up as the negative bus. And when I start the simulation, remember both of these multimeters are measuring relative to ground. You see that this one is measuring 5 volts, but this one is measuring negative 5 volts. And for many op amps, it's going to be set to plus or minus 15 volts in a lab. But, excuse me, so again, this is what I mean by a split positive and negative power supply. I have 3 terminals, 0 or ground in the middle is what everything else is referenced to, and then I have positive 5 volts or 15 volts if I dial that up on one side. See if it lets me type that in here in Tinkercad. There we go, 15. So I have plus or minus 15 volts, and that is what I am going to be feeding to the power plus and power minus pins on my op amp. Now, you have to be careful not to get the power pins mixed up with the input signal pins, and depending on what textbook or software you're using, these might be labeled differently. You see in the data sheet, those power pins are labeled V plus and V minus, whereas Tinkercad calls them power plus and power minus. And in my circuit diagram theory playlist, I used just plus and minus, and actually did use V subscript plus and V subscript minus to indicate the input voltages, not the power voltages. So again, different conventions in different places. Be careful about how you are wiring the physical op amp. The best source is going to be the datasheet when you're building something physical in a lab. In this case, in Tinkercad, I need to connect negative power to this pin here. So you can see I kind of have things backwards on the breadboard. It would have been maybe more convenient if I had mirrored everything and done negative power over here and positive power over here. Now I just need a longer jumper wire going here from, I have to stop the simulation before it'll let me add a wire. Going from the negative power pin here, and then the opposite for positive power. I'm going to need that to go over to the other side. So again, the way I have everything wired up here is all nice, kind of left to right, just the way things were ordered in Tinkercad. That makes this a little more wonky with the longer wires down here. If you wanted to do shorter wires on your physical breadboard, you'd have to reverse how you have everything wired up here. So again, electrically doesn't matter, all the connections are the same, but physically in terms of how neat you are keeping the circuit, it does matter. Now, that is just wiring the op amp. Now that you have it powered, you're kind of at the point where the world is your oyster in terms of which op amp circuit you are going to build. And maybe this is going to depend on what lab you're doing, where you're asked to build something specific, like the ones I have covered here, inverting and non-inverting amplifiers, or differentiator or integrator, current to voltage converter. I don't even remember what else I have in this playlist. Again, tons and tons of op amp circuits. You can do a comparator, differential and summing amplifier. I am probably just going to go through and do an inverting amplifier, because that is one of the simplest and earliest examples you will usually see, where you just have 2 external resistors labeled RF and RS in the diagram here. So the feedback resistor RF goes from the output terminal of the op amp back to the inverting input, and then the source resistor RS goes from the inverting input to whatever your source is, which is just labeled as a generic voltage source here in the diagram, but that is going to be a function generator usually in a lab. So you can send something like a sine wave or triangle wave into this op amp, and then per this equation, the amplitude of the output voltage is going to be amplified based on the ratio of these 2 resistors, but it's also going to be inverted. So it'll be negative when the input voltage is positive and vice versa. And again, this whole theory playlist goes through all the different equations for all these different op amp circuits. We have one more connection there. The positive or non-inverting input is going to be connected directly to ground. So I might bounce back and forth. You're going to need to reference this diagram as we are building this on the breadboard, so I'll be going back and forth between these 2 browser tabs as I do that. So being patient and doing this carefully, one connection at a time, because you can blow up op amps. Releasing the magic smoke from an op amp is sort of a rite of passage in many electronics labs. Thankfully, you can't physically blow things up in Tinkercad, so that is a good place to practice. There is no right order to do this. It's whatever makes the most sense to you when building. I am going to first connect my non-inverting input to ground. Again, that's labeled in plus in Tinkercad, and the way I have my buses labeled, I can just use my bus is wired. I can just use a short jumper wire to connect directly from here to that one. I'm going to make that black for consistency. I could have wired it over to this one because, again, those are connected with a jumper wire, but it's a little more convenient to do like that. Now, I am also going to need that feedback resistor going from the output to the inverting input. So that is from over here, output to the inverting input here. Now, with a physical breadboard, it's a little easier to just kind of bridge that gap with the resistor going directly across the op amp, but Tinkercad only lets me rotate things in, I don't know, just some discrete angle here, and I can't really get the resistor exactly where I want it there, so I am going to do this. I'm going to route the resistor, so one end of the resistor is connected out, and I'm going to use a jumper wire to connect back over to the inverting input like that, and maybe I'll change that to a different color that I'm not using for any of my power connections, so I'm going to make that green. So what I just added there is, again, the equivalent of this resistor in the diagram, where I have gone from the output back to the input. It's okay to use extra jumper wires to make that connection if needed. Again, you want to keep your circuit as neat as possible visually so it is easier to debug and trace all the connections later. And again, note how the physical layout of the resistor does not have to match its physical location in the schematic, right? So in the schematic, I have the resistor up above the op amp. Here, I could do that if I wanted to. If I really wanted to try and match the diagram, I could say I'm going to have my feedback resistor up there, use a jumper wire here to connect to the inverting input, and another jumper wire over here to connect to the output. So again, even though I don't have the triangle symbol for my op amp, that kind of matches the layout of the diagram a little more. Totally personal preference. Again, it is just important not to get the physical layout confused with the electrical connections. This is electrically equivalent to what I just had with that resistor over here. Putting it up there did not change the electrical connections. It just changed the physical location, and maybe that's a little neater or easier to trace the connections and debug. Matter of personal preference, but just keep things neat. Don't let it get too messy, because as you connect more things, it's going to get harder and harder to trace all the connections. All right, after connecting that feedback resistor, and again, you don't necessarily have to do that in this order, I need my source resistor, which is going to go to my voltage source, which I'm going to hook up as a function generator. So I need that going from, again, also the negative or inverting terminal, depending on the size of your resistor, how things lay out in Tinkercad here. I'm going to just send that resistor down to this terminal. Again, I, in this case, don't want to have it going left to right like this, even though that matches the diagram, because that doesn't really give me a hole to put it in over here. And if I crammed it all into the same row, then by bending the leads on a physical resistor, then I'd be shorting the leads together. So I'm going to make this one go down like that. So one end is connected to the inverting terminal. The other end is just in an empty row in the breadboard. And then I'm going to search for the function generator here in Tinkercad, which again kind of reproduces some of the basic functionality of what you would expect in a benchtop function generator, where I have different waveforms and can adjust the amplitude and frequency and offset. I'm going to connect the negative terminal of the function generator to ground. Again, that is my zero or reference voltage that I want everything else to be referenced to, so common ground for the whole circuit. And I'm going to connect the positive terminal of the function generator, that is going to be the input voltage to my circuit, to the same row as the other end or free terminal of this resistor. And if I go back and check the diagram, we see I have one terminal of that resistor connected to the inverting terminal of the op amp, and the other end connected to the positive terminal of the voltage supply. So, okay, I have connected my function generator, but I cannot really see anything yet. That is where the oscilloscope comes in, which, again, if you're doing this in a physical lab, you are likely going to have a benchtop scope with multiple channels, so you can view everything on one screen. Tinkercad just has this very rudimentary oscilloscope with two connections. It doesn't have multiple channels, so if you want to see both the input and output voltages to the op amp, you are going to need two scopes. So let's connect one first, just so we can see the input voltage So again, we're going to give everything a common ground, connect the negative wire from the oscilloscope to the ground bus. And for the positive wire, which this is going to be a probe with a physical oscilloscope in a lab, we're going to connect that to the same row in the breadboard as the positive wire from our function generator. So now, when I start this simulation, that should give me a view of my input voltage to the circuit. Now, the simulator in Tinkercad, the controls for the oscilloscope aren't great. There aren't really any knobs you can turn, so I'm going to go in and maybe increase this to 1 second or something because I was zoomed in. And one of the downsides of this, it sometimes gets a little laggy when you try to update the oscilloscope. I am trying to adjust the time or zoom out a bit so I can see my square wave signal here a little better. And you can see I just turned the frequency way down, and now there is kind of this weird lag on the screen as it updates. So I might pause recording here and see if I can get this to update and actually show the square wave on the screen, because again, you can see, say if I adjust this to a 1 hertz signal with 10, there we go. Again, very laggy there, but it's kind of gradually catching up to show the 1 hertz signal on the screen here, where I have 1 second per division on the oscilloscope. Okay, so I take that back somewhat and apologize. Maybe it was because it was actually taking 10 seconds to scan across the screen, and that's why it seemed like it was lagging. Now I have this set to a 1 kilohertz signal with 1 millisecond per division, and I'm seeing the changes a little faster like I would expect to when I tweak the knob here. Anyway, that is just looking at my input signal, and the whole point of all these op-amp circuits is that you are somehow transforming the signal, again, amplifying it, differentiating it, adding two voltages. There's tons of different options. So we want to add another oscilloscope. Where again, doing this in a lab, you'd probably just have one scope with multiple channels. We don't have that option in Tinkercad to look at the output voltage. So again, negative wire of that oscilloscope goes to the same ground as everything else in the circuit, but the positive wire is going to go up here to our output. And now when we run the simulation, in this case I had built that inverting amplifier, but my two resistor values are the same, so it's not actually going to be changing the amplitude of the voltage. But if I go ahead and change this, say, to a 2 kilo ohm resistor instead of 1 kilo ohm, then from my formula here, RF over RS, I should see the absolute value of that amplitude doubling when I look at the output voltage. So if I run the simulation here, again, the controls for the oscilloscope aren't great, but you may notice that the auto-scaling y-axis, I can't really control the offset here, which is kind of strange, but the scale here on the y-axis is 40 volts instead of 20 volts. So I'm zoomed out. Even though these waves look like they are the same height, I have doubled the output of my amplitude or voltage because of that resistor being twice the other resistor value. You can see that the other annoying thing about having two different scopes is the time axes here are not in sync. So if I drop this one down to also be 1 millisecond per division instead of 100, again, kind of laggy there, but we can see if I get these lined up, something I forgot to mention earlier, by default, the function generator has a positive DC offset, so I'm going to go ahead and change that to 0 real quick. So my input voltage is now centered around 0, and we see that we would expect these to be out of phase since it's an inverting amplifier, and we know, actually I switched to a different video here, but we know from the equation we saw earlier that the output should be negative when the input is positive and vice versa. But since these have different x-axes that aren't in sync with each other like you would on a single scope with multiple channels, we can't actually see that here. It looks like these signals are in phase if you assume the x-axes of the scope screens are aligned, but they're not. Tinkercad is just triggering these separately and the axes aren't lined up. So if we could see these on the same screen with multiple channels on a physical benchtop scope, then this signal would be negative when this one is positive and vice versa, but we're not seeing that in Tinkercad. So again, you have to be careful with the multiple scopes. You can't adjust the y-axis. There's no cursors for either manual or automatic measurement of period or amplitude or frequency or any of that, so you're kind of just limited to counting divisions for either time or voltage. So again, much more limited than what you would have with a real benchtop scope, but we have now set up a basic op-amp circuit and lab here in Tinkercad. where we have our split positive and negative power supply. We have the op amp set up with power on the breadboard and external components, in this case 2 resistors to build that inverting amplifier. We have the function generator feeding the input voltage to the op amp circuit, and the 2 oscilloscopes set up to measure the input and output voltages. And now, once you have most of this infrastructure set up, you only need minor changes to build a different op amp circuit. For example, swapping one of the resistors for a capacitor to build a differentiator or an integrator instead of a amplifier. So you might need to rearrange your probe connections a little bit. So for example, I could just pop this resistor out and swap a capacitor in, but depending on exactly which circuit I'm building, your input voltage might move around or something, so you might need to move your oscilloscope and function generator probes. But for the most part, you can leave most of the exterior equipment and power connections in place, and it's just a matter of swapping around the connections to the inputs of the op amp to build different op amp circuits. I am not going to demonstrate all of those in this video because we could easily fill another 15 minutes swapping things out to build integrators and differentiators and summing amplifiers and all of that stuff, but kind of as an exercise for the viewer, challenge yourself to maybe go pick a different circuit from this playlist and see if you can swap the external components around, and then go ahead and look at the changes to the output waveform as you play with different input waveforms. So again, if you're taking a derivative, then the output's going to be different depending on whether your input is a square wave, a sine wave, or a triangle wave. That is going to be it for this video on op amps. As time allows, as always, I hope to continue this series, probably moving on to diodes and transistors next. So if you are not already, subscribe or make sure you bookmark this video or playlist or something so you can get a notification when I come out with the next video in this series, or depending on how far in the future you're watching this, the next video might already exist. So go ahead and check out the video description for a link to the playlist so you can find the other videos. Thank you.